Now we're going to do Bayes Theorem by Thomas Bayes from 1701 to 1761, also known as Bayes' rule or Bayes' law. However, Laplace independently rediscovered Bayes' work and has made it into what it is today. Bayes' theorem is to probability what the Pythagorean theorem is to geometry. So first we'll start off with an equation. Alright, so what we have probability of B given A is going to be equal to the probability of A given B times the probability of B all over a sum of probabilities. And now you can see this is going to come from the total probability rule. So P of A B piece of B J. Oh, sorry, I. Okay, and if we want to write this out with some words, it's the probability of the state given the sample is going to be equal to the probability of the sample given the state times the probability of the state all over sum like 1 k of probability of the sample state, and we must have some lines here. That's the probability of the state. Okay, and clean up the equation a little bit, make it look a little nicer. The probability of A given B is going to equal the probability of B given A times the probability of A all over the probability of B. Okay, and this will generally be what we will use, and solve most problems we'll have to use this as well. Okay. Now what I'd like to do for you is derive Bayes' rule. Okay, so first I'm going to use our conditional probability, and we're going to see that the probability of A given B is equal to the probability of A and B over the probability of B. Okay, now what also is true is that the probability of B given A is going to equal to the probability of B and A over probability of A. Okay, now if the probability of A and B is equal to P times, let's write this out differently. A given B and the probability of B, well then it's also, because of some of our rules, it's also equal to the probability of B given A times the probability of A. Okay, so using this here, we can get Bayes' theorem. So solving for the probability of A given B, we get the probability of B given A times the probability of A equals, or over the probability of B is going to equal the probability of A given B. For an example, a construction company employs 3 sales engineers, engineering 1, 2, and 3. They estimate that the costs would be 30%, 20%, and 50% respectively for all the jobs bidded by the company, and that only one engineer estimates the cost of the bid. So 30% of the jobs were estimated by engineering 1, 20% by engineering 2, and 30% by, or 50%, sorry, by engineering 3. So we see example 1. We have the probability that engineering 1 did the job is going to be 30%. So 0.3. Probability that engineering 2 did the job is going to be 0.2 for 20%. And the probability that engineering 3 did the job is going to be 0.5. Okay. So now we have probabilities that are given for us, stating that if there was an error, we would know that it was either done by engineering 1, engineering 2, or engineering 3. So the probability of an error, given that it was done by engineering 1, is 0.01, which means that out of 100 jobs, he's going to make an error bidding or doing the bid on 1 of the jobs. For our engineering 2, his was 0.03. That's 3 out of 100 jobs he makes an error. And for engineering 3, 0.02. And that's 1 out of 50. He makes an error. Okay. So now what we want to find is if a particular bid results in a serious error, what is the probability that the error was made by engineering 1? What that really means is that given that engineering, or given that there was an error, what is the probability that it was engineering 1? So engineering 1, given there was an error. Okay. So using conditional probability, we could figure this out pretty quickly. So we know that this is equal to the probability of an error, or engineering 1 and error, over the probability that there was an error. Okay? And for this guy here, that conditional probability says that the P of error 1, or sorry, of error, given it was engineering 1, times the probability that engineering 1 made the bid. Okay, divided by, and now here is where it gets kind of long. We're going to have the probability of error given engineering 1, and the probability of engineering 1, plus probability of error given engineering 2 times the probability of engineering 2, and then plus the probability of error given engineering 3 times the probability of engineering 3. Okay? Now, plugging in some numbers, we will find 1, given there's an error, is equal to point 0.1, sorry, times 0.03 divided by 0.01 times 0.3 plus 0.03 times 0.2 plus 0.02 times 0.5. Okay? And now that gives us a value equal to 0.158. That's 15.8% chance that engineering 1 did the job, given there was an error. Okay. So now part B asks us, which engineer is most likely to be responsible for making the serious error? So this tells us, the probability that engineering 1 made the error, or engineering 1 made the bid given that there was an error. So all we need to do is we need to do this for engineering 2 and engineering 3 and figure out which one has the highest probability. So only difference there would be switching the top. So for engineering 2, it's going to be 0.03 times 0.2 over the denominator, and it would be 0.02 times 0.5 for the other one, and we'll do that here. Okay. Now, both of these are going to give us 0, 1, 2. We get a 0.31579. And for engineering 3, who actually bids on half the jobs, gets a 27. Oh, whoops. The 52. Alright. So this one says 52% chance that he made the error, 15.8% at engineering 1, and 31.5 for engineering 2. And of course, since they're the only ones that made bids on these jobs, then these probabilities here should add up to 1. So I'm going to take 0.52632 plus 31.5 plus 0.158. I get 1. And this is an approximation, so. Alright, so engineering 3 will be the one most likely responsible for making a serious error.